3q divided by 4 pi epsilon 0 r squared. So in this case of spherical symmetry, we have that the potential V equals E times R. But we know that E cannot exceed 3 million volts per meter. And so that gives you now a limit on the potential that we can give the Van de Graaff. So if you substitute in here 3 million volts per meter, you can calculate what potential you can maximally reach for a given sphere with a given radius. And if we here have the radius and we here have the voltage, then if the radius of the sphere were 3 millimeters, then you could not exceed a voltage of 10 kilovolts. If you did, you would get this automatic electric breakdown. You would get a spark. If you have a sphere of 3 centimeters, that would be 100 kilovolts. And our Van de Graaff, which has a radius of 30 centimeters, would therefore be 1 million volts. You could not exceed that. And in practice, in fact, this one doesn't even make it to 1 million volts. The sphere is not perfect. There are imperfections of the sphere. There are areas which have, so to speak, sharp points. And so we won't make it to 1 million volts. We get a breakdown maybe at a few 100,000, maybe 300,000 volts. You can now also calculate what the maximum charge is on the Van de Graaff, because if the maximum potential is 300,000 volts, you know the radius is 0.3 meters, so you can calculate now what the maximum charge is that you can put on the Van de Graaff using that equation will give you 10 microcoulomb. And so the maximum potential for our Van de Graaff is of the order of 300,000 volts. So this gives you now a feeling, a quantitative feeling for numbers, for what the, shall I put this down? So this gives you an idea of what our Van de Graaff can do. And later we will understand how the charge gets there. But at least you have some feeling now for potentials and for the charges that are involved. Here's my Van de Graaff, and I approach the Van de Graaff with a sphere which is connected to the Earth, and if this Van de Graaff has positive charge on it, then this sphere will become negatively charged through induction, and so you get field lines which go from the Van de Graaff to this object, always perpendicular to the equipotentials, so they go like this, and so the electric field here will probably be the strongest, and so the spark will then develop between this sphere and the Van de Graaff, provided that you are close enough, so that you do achieve an electric field close to this sphere of about 3 million volts per meter. And I will show you that later. You will see more sparks today than you've ever seen before in your life. But I want you to appreciate a little bit more about the sparks, about lightning, before I demonstrate that, so you get a little bit more out of it. If I approach the Van de Graaff not with the sphere, but I would walk to the Van de Graaff being very courageous like this, I'm also a pretty good conductor, I'm also connected with the Earth, then the chances are that the spark would develop first between my nose and the Van de Graaff, because that is the smallest the sharpest curvature, the smallest radius, where certainly my head would be a good candidate for being hit first. If I approach the Van de Graaff like this, with my hand stretched, then chances are, of course, that the sparks will first develop between my fingertips, because it's a very small radius, and they're very close to the Van de Graaff, and so that's where the discharge will occur. And so before we will enjoy some of this, you will enjoy it, I will enjoy it less, I want to talk a little bit about lightning with you first. Because what you're going to see, in a way, is a form of lightning. There are 400,000 thunderstorms every day on average on Earth. 400,000 thunderstorms. There are about 100 lightning flashes every second. The top of a thunder cloud becomes positive and the bottom becomes negative. The physics of that is not so easy and probably incomplete. And I will not go into the details of the physics, but it does have to do with the flow of water drops. They become elongated, they can become charged because of friction, and they can break off, and they can transport charge. I will simply give you some facts. And so I will accept the fact that the cloud is going to be charged. This is the cloud. Positive at the top, negative at the bottom, and here is the Earth. Because of induction, the Earth, of course, will therefore become positively charged here. And so we're going to see field lines, electric field lines, which go from the Earth to the cloud, always perpendicular to the equipotentials, something like this. I'll give you some dimensions. This may be something like 5 kilometers. This vertical distance, d, is about 1 kilometer. These are typical numbers, of course. It can vary enormously from thunderstorm to thunderstorm. And this height is something typically like 10 kilometers. And this allows us now to make some very interesting calculations to get some feeling for the potential difference between the cloud and the Earth. That's the first thing we can do. If we make the simplifying assumption that the electric field is more or less constant here, it's like having two parallel plates where the electric field is constant between them, then the potential difference, delta V, between the bottom of the cloud and the Earth is simply the electric field times the distance d. So this becomes E times d. But if the breakdown occurs at 3 million volts per meter, by the way, that's dry air. When there's a thunderstorm, it's probably not so dry. But let's take the 3 million volts per meter. So we get 3 times 10 to the 6. That is for E. And the distance between the cloud and the Earth, let's take 1 kilometers. So that's 10 to the 3rd meters. So we get of the order of 3 billion volts between the Earth and the clouds. And the values that are typically measured are several hundred million to 1 billion volts, so it's not all that different. You expect that the potential is probably less than what we have calculated, because clearly these are not flat surfaces. There are trees here on the ground, there are buildings on the ground, which are like sharp points where the electric field will be locally higher, and so you will get a discharge at these sharp points first, and that means the potential difference between the cloud and the Earth could then be less than the 3 billion that we have calculated here. But it's only a back-on-the-envelope calculation. The details of the physics of the discharge, very complicated. But I want to share with you some facts without giving detailed explanations. The start of the lightning begins when electrons begin to flow from the cloud to the Earth. They form a funnel which is about 1 to 10 meters in diameter, and we call that the step leader. The step leader moves about 100 miles per second, and so it comes down in about 5 milliseconds. 5 milliseconds from here to here, and it takes about half a Coulomb to the Earth. Half a Coulomb for about 5 milliseconds, that means the current is about 100 amperes. The step leader creates a channel of ionized air, full of ions and full of electrons, which is an extremely good conductor.